Okay, so welcome back, and now we'll be studying in the simulations of robotic system and other virtual agents. So we've already seen a lot of simulations, done a lot of simulations as a part of the laboratory component, and the artificial agents did absolutely amazing things around, and they moved around, and they were interesting stories that they narrated, looked as great animations. And using that, of course, you could do in things like testing the how many people can exit the building. Do they cause a chaos? Do they cause a congestion? Do they fight, or they amicably bypass each other? How much congestion can I have? When should the classes get over? When should the others start, so that there's no chaos? And all the wonderful things. But now we go more robotic in nature, and that's really a wonderful buzzword that is floating around. That we want to simulate robots, we just want to do it, and the applications are absolutely many. First of all, what we also correlate to, that we have a limited number of robots in the labs, and many undergraduates would like to do projects, and we cannot give them expensive robots. So it becomes easy that work with the simulations only when you are absolutely great in simulations, then we give you the real robots to play with. Now, sometimes it so happens that even though we have real robots, I may be doing a research in underwater robotics, I may be doing a research with robots climbing the Mount Everest, or maybe the robots which go into fire and all those wonderful applications. And I may not be having those situations out in my lab. Definitely there's no Mount Everest nearby, and definitely there's no ocean nearby. So how do I do it? I do it using simulations. Many other times when it comes like situations like fire, even we people are extremely scared. Expensive robots will get damaged. So we try to test the robustness and those hard scenarios by using simulations alone, where simulations tell us that will this robot be able to do as it's promised or not. Sometimes it's more interesting. Sometimes you really want to test your robot under extreme circumstances, and you're not willing that you sacrifice your robot which may malfunction. And when the robots malfunction, it's like breaking a very, very, very expensive toy. You do not know what are the costs of repair. So the simulations happen to be a great boom. Now, all this was still pretty much a few years ago. Now the situation has changed because more people talk about machine learning, reinforcement learning on the robots. And if you do it on the real robot, you can only maybe buy one or two of them, and they have battery limitations. But then if the robot is simulated, we've got a central computing facility with endless number of cores, endless number of GPUs. Let tens and thousands of robots learn in a simulation environment in parallel in all the multiple cores. So I don't need to do anything. They are learning. They are learning day and night. They are learning extreme scenarios, extreme circumstances that I cannot even try with the real robots. So that makes it a great boon for machine learning. A robot that learns as a physical robot will only have one robot, which will be limited by so many factors, the number of scenarios that we can produce. But a simulated robot can really test everything. And imagine that, what if I'm learning for either multi-robot or robot versus human? How does a robot avoid human? I may have one robot, and my research scholars, my project students may not be willing to really travel as the robot is going around and learning. In simulation, I could create virtual avatars of them. So simulations really do help you learn in parallel Can't talk about self-driving cars. So, how many miles can an actual self-driving car test on a everyday basis? That's limited, 100 to 100. There's only one vehicle. How many self-driving cars can I test in simulation? I can test hundreds and thousands of miles every hour. I've got all the GPUs, I've got all the compute and everything. And that's why the focus is now more towards simulations. And what makes our discussions on simulations now different is that now I want to test robotic systems and therefore I need to be more realistic. So like a virtual agents could fly, could take unreasonable paths, could display unreasonable behaviors. That shouldn't be possible. Only those things should happen that my robot can physically do. It cannot jump, it cannot fly, it cannot do all those things. It's limited by speed. So those are the factors that I'll have to take care about it, or I'll be cautious about the accuracy of my simulation. So the real system should behave as closely as possible to my simulated one. Now talking about realism, so let's start simulations. And the first thing that of course you'll have to do is to create an artificial environment. So I've been drawing maps like this for pretty long. And then I also tell you that this is me, of course, a better form of me, and this is my research scholar moving out as a GURP. And then there is a real door at the entrance of this, and that rotates. So when I talk about physical robot, everything is there over here. You can just you can just get a robot, everything is there. But then with the artificial agents and with the robots, you really have to create this environment using whatever 3D drawing tool you may like. Now, you're lucky if what you are doing is completely artificial and it's completely synthetic. So then what you could do is to take any library and that will give you an empty floor plan like this. And then you can say that, okay, let me become an architect and let me create in all the cubicles around over here as the architects do. And you add all these doors and everything. What you can also do is to go shopping, which is digital shopping, and buy some tables and some chairs all the way around over here. And it's digital shopping, so 3D models of all these tables and chairs exist in all the popular formats. So you can actually take them from any 3D library, CAD model, or whatever, and you can just drag and drop into your simulator. So you're the architect of this virtual world, it's your world, so you should be able to just drag and drop things around, and similarly you should be able to drag and drop real robots around. So that's what you do. You should be able to drag and drop plants around. You should be able to drag and drop whatever other objects. So you should be able to drag and drop lights around. You should be able to drag and drop everything that you like around, which is, I like a laptop over here. I should be able to add that. So it's just drag and drop, and a good simulation will, of course, provide all these facilities. And internally, how is it stored is, of course, the object and its pose. So the poses, 3 translation axes, 3 rotation axes. So you've got object 1, object 2, object 3, and so on and so forth. Now, it turns out that it's actually pretty interesting. So let's take in a specific example. So I added a table, and I'm very bad at drawing tables. And over the table was a manipulator. And Over the manipulator was an end effector, and at the end effector was a glass of water. So, and there were some books. Now, what's interesting is that if I move the table by 1 meter, all these entities actually move. And therefore, what I say is that the table is connected to book 1. Book 1 is connected to book 2. So this is your book 1. Because if I move book 1, all these books move, which is connected to book 3. And so on. And similarly, table is connected to manipulator, which is link 1. If I move this link, then everything moves, which is connected to link 2, which is connected to link 3, which is connected to link 4, which is connected to end effector, which is connected to the glass of water. So I've got the transformation over here. Where is the table in the book? Let's say T1. Where's the book 2 with book 1? So let's say, where's book 2 with book 3? And so on. So, and of course, everything is in the world. So, everything is in the world. So if I move this transformation, what really happens is all these objects also move. So if I need to calculate the pose of book 3, I use the same mathematical foundations of robotics principle, that the pose of book 3 is this transformation times this transformation times this transformation times this transformations. And similarly here for this thing, and this of course has a special name from the past course on manipulators. It's a kinematic chain. And calculating, given all these joint angles, calculating the position of the end effector. So calculating this position with respect to your table is also what's called as the forward kinematics problem. Now, overall, this is what's called as a object hierarchy. So again, saying that your simulation tool should allow you to really drag and drop items, but when you drop items, you really should be able to specify where in the object hierarchy are you putting it up. Are you putting it on the floor, which is on the world? Are you putting it on some table, in which case it gets attached to it? Are you putting on something which is already on the table, in which case it gets attached to that? And any simulator will store it in the form of an XML file. So this is only to look at it. This is what's stored as XML file, where the XML file contains two things. One is the 3D model, and the second is what is the transformation. So the vertices, this become the 3D model, the CAD file or the 3D model file, and then between every two, if there's an edge, you store it in the form of a transformation. Now the end effector actually holding a glass is interesting, because the glass is what is called as a fixment to the manipulator. So I say the glass is affixed to the end effector. The end effector, of course, is affixed to the last link as per the manipulator principles. Now, all this is okay, but what do you look at the screen? Your screen is 2D, your computer screen is not 3D, and therefore every every simulation library will actually provide a virtual camera, using which you can project this 3D plane into a 2D image plane. So if I take it inverted, I'll have to take focal length distance away. I'm taking it direct. So after focal length distance, whatever is the projection on this, many things will be visible, many things will not be visible. You should be able to look at it. And this virtual camera can be moved typically by using a combination of keyboard and mouse. So this virtual camera has 3 translatory axes, which is X, Y, Z. So you move it with the keyboard, where it depends upon whether you've hit the control, whether you press the shift. So you can control each of the 3 axes. You have 3 rotation axes. And of course, you can vary the focal length, which is typically a constant. So you'll have to go into the configuration file and the image size. So which is also the field of view of the camera. So it's an interesting exercise, making a simulator. So you drag and drop all items from the object recognition library, where of course dragging and dropping actually makes this, and this is rendered onto the screen. Now what you do is that with every model you actually project it on this camera. You know the extrinsic parameters, you know the intrinsic parameters, so you project every object as per its model on the 3D camera and just show the model on the screen. And you can have any number of virtual cameras. There's no shortage of virtual cameras. And how to project all these CAD models, all these 3D models, all this wonderful colors, all this light sources into a virtual camera is not a part of this course. It's already a part of a previous course, which is a course on graphics, and we call it as a graphics library, which projects all these 3D models into a image plane as per the camera intrinsics as intrinsics. So all the polygons, ultimately what's a 3D model? It's some meshes, it's some polygons, it's some material. There are some lighting properties, some illumination properties because of the lights. The most common 3D library, of course, is what is the OpenGL, the Open Graphics Library, which does this part. And we still haven't come to any kind of programming. So right now we're just being architects, being designers. And that's why designing actually became very popular, because of the need of to create all these synthetic scenarios. People would really hire designers to make in cool environments. The 3D designers do a much better job than what most robotists do. Now, sometimes it's more interesting. Sometimes you say that this is my lab, I cannot give in expensive robots, but I want everything to work exactly as it is. Then you need to hire companies and startups who make rich 3D maps from physical world. So essentially they do a high precision and accurate offline simultaneous localization and mapping. Previously, when we looked at SLAM, everything was happening real time. What these companies would do is they'll make the robot, which is a high precision robot with all the sensors in the world, actually go at painfully small speeds, and every few minutes it collects some gigabytes of data. So you collect some terabytes of data in a single run of the entire laboratory. And then I talked about the online optimization, the problem of SLAM. These libraries do an offline optimization. So for days together, you can run those optimization. And what you get is a dense pixel-wise map, what we showed you in the last lecture. And then, of course, what these libraries do is they try to identify entities from these labs that, okay, this is most probably a table, and this is most probably the curvature of the table, this is most probably the position and the pose of the table, this is most probably the specifications of the table. This is most probably the illumination properties of the table. They extract all that information out and they replace it with the same table with all those properties as a object hierarchy. So you basically do a rich HD slam, and of course, a lot of startups, a lot of vision problems are towards people like us who would like to make a rich high definition map of our institute so that we can test the robots on our virtual campus map and hope that the real robot will perform exactly the same thing. If you've got people, then of course they are rich 3D scanners. So I stand in front of a rich 3D scanner and the 3D scanner makes in a complete avatar of me, identifies, this is a manipulator, identifies all the sockets, all the joints, all the links and their properties. And that's how you create a virtual avatar of me. And that's how you create a virtual avatar of Door, and so on and so forth. So you do a rich HD slam and get all those properties.